Okay. Hello, judges. Our project is machine learning-based accessible mobile app for activity recognition and freezing of gait monitoring in Parkinson's patients. So just for some background information about Parkinson's disease, Parkinson's disease is this progressive neurological disorder that affects movements, and it's caused by the death of these nerve cells in the brain that help regulate movement, resulting in a lack of dopamine. Symptoms include difficulty with movement and balance, changes in speech, and freezing of gait, or fog, which we'll elaborate on later. And they vary in severity, but those are the most common. Currently, the diagnosis process for detection is extremely expensive, so we wanted to look towards a more accessible approach towards detecting Parkinson's. So more on freezing of gait. This is when an individual's feet get stuck to the ground, making it impossible or very difficult to take a step. And it happens when you try to initiate a step or when you attempt to turn while walking. And this is a very evident symptom of Parkinson's and is the most widespread. So it can potentially be detected through machine learning trained on accelerometer data of body movements. And in the past, these were through accelerometers attached to people's hips and legs. And what's different is with ours is that it'll actually be an app so that it'll just sit on somebody's thigh and it'll get accelerometer data just by using what's available in a phone. Also using an app would allow patients to track how many fog episodes occur per day to evaluate if a medicine is working. And again, it would just make it more accessible. So here's the diagram of freezing of gait. As you can see, it varies in severity, and at the high end, it can result in complete akinesia, which is basically when the leg is completely frozen up and you're unable to have any leg motion. And then we'll just play a little bit of the video here so that you can see what it looks like.
Okay, so now let's start with ensemble methods. For this project, we use two ensemble methods, starting off with AdaBoost, or adaptive boosting. And this is an ensemble algorithm that combines weak learners to create strong learners. Weak learners are essentially simple models that perform just a bit better than random guessing. Weak learners include decision trees with small number levels, or they are simple regression models. The adaptive boost iteratively trains these weak learners on the same dataset, and they provide more emphasis on the samples that were misclassified by the previous models. What this allows is that this allows the subsequent models to focus more on difficult samples that were not classified properly. And it hence improves their overall accuracy of the ensemble. And this shows an illustration of the AdaBoost model. It talks about all the different frames and the iterations that are included on this. Moving on to the, okay, now let's go on to the extreme gradient boosting, or the XGBoost. And this is a machine learning algorithm that can do classification and regression problems. The main idea behind the XGBoost is to create a series of decision trees, and these decision trees are used to make predictions on the new data. The XGBoost has several features, including speed, regularization, handling missing values, and interpretability. The XGBoost is designed to be fast and efficient. It has built-in regulation techniques like R1 and R2, L1 and L2, and it can handle missing values, as it can automatically handle missing values without the need for imputation techniques. And it provides information on feature importance, which can help in understanding the underlying data patterns. This shows an illustration of the XGBoost model. So yeah. Now moving on.
So onto the background for the Fourier transform. The Fourier transform is a technique where we convert a signal from a time or spatial domain to its frequency domain. And how we do this is by decomposing a signal into its constituent sinusoidal components. Now, this is really, really important to our project because Fourier transforms can help to identify periodicities and trends in a time series. And this can be used to build more accurate forecasting models for our project. So in our project specifically, we use Fourier transform to compute two different sets of features for an activity recognition model. Now, moving on to the image for the Fourier transform. For example, after a Fourier transform, we can see that a cosine wave is represented as a single frequency, whereas a sine function is represented as a uniform band of frequencies, and so on and so forth.
The problem we wanted to solve was finding a more accessible way of identifying, monitoring, and alleviating Parkinson's disease by detecting freezing of gait via a smartphone app and through using machine learning. Some of the goals that we wanted to solve for was firstly being able to accurately predict fog events using the AdaBoost model, being able to accurately predict user activity after training the XGBoost model on activity recognition dataset, basically meaning that it will tell when somebody is sitting or when somebody is standing and what action they're doing, and to display the activity a user is doing at any time and then vibrate if fog is detected when a user is moving and record instances of that fog in the user. And in addition to that, we also wanted the app to be able to call emergency services in the case of a severe fog event. That way it could call for help in case someone really needs it.
So why are these vibrations effective for handling fog? Pereira et al. Has shown that that vibrations may be effective in shortening these FOG episodes. Now, the app ideally will vibrate when detecting fog to potentially help alleviate it. Now, as shown by Pereira et al., there was a statistically significant difference of fog duration between the no vibration or control group and the vibration group. So onto our progress to date. We finished cleaning and filtering the DAFnet database and have performed exploratory data analysis. We also finished implementing a sliding window with a 50-row width, and this is 0.75 seconds of accelerometer data, and it computes over 150 features based on 3 initial features, which are acceleration from the 3 axes. Now, models have been trained on both the fog dataset and the activity recognition dataset, and the app implementation of both of these 2 models is complete, and they have both been tested. Now, we would like to add a vibration app feature for the reasons we said in the past couple slides. We would like to finish and add the app UI. We would like to implement active learning just so that the model will perform better, implementing a call or text feature to the caretaker to make sure that everything is safe and that the person who's using this app is better protected, and finally to publish the app in the App Store.
Okay, now let's talk about our approach. Starting off with the materials. So we used the DAFnet fog dataset, and this was the basis for our project. Then we also used the WISDM activity recognition dataset. For the app, we used React Native JS CLI plus Expo CLI. We also used Expo sensors, Python Flask, and a Google Cloud Engine for the app.
All right, so moving on to the fog dataset and pre-processing. So once we loaded in the dataset from the DAFnet dataset from UCI, this is an image of our dataset where you can see that we were mainly focused on 3 features, which is UHF, UV, and UHL, which are the horizontal forward acceleration, thigh acceleration for vertical, and finally horizontal lateral acceleration. And the last column actually shows an annotation. And this essentially indicates if a certain acceleration reading occurred during a fog event, which is represented by a 1, versus during a non-fog event, which is represented by a 0. And this data has been sampled at 15 milliseconds for 36 minutes. So we couldn't really use a classical machine learning approach since this is a time series dataset. So instead, we decided to go with the sliding window approach, where essentially a window of 50 data points will slide through the entire dataset. And the TS-Fresh library will generate high correlational features from each window of the dataset. And in order to decide the annotation for each window, we decided to go with a threshold of 10%. So if 10% of the annotations in the window are a fog, then we would classify the entire model as a fog event. And this allows models to predict fog in advance, since If there's a small number of annotations, which are fog, it likely occurs just milliseconds before a fog event. So moving on to loading in our activity recognition data set. This is a screenshot of our activity recognition data set. And as you can see, the data set was compiled from activity from 36 users of walking, jogging, sitting, standing, and finally going upstairs and downstairs. But we didn't really need the model to predict upstairs and downstairs, but we really needed the model to predict when the user was actively moving. And this was sampled at 50 milliseconds per row. So this is an example of our data set. You can see that walking was the most common annotation in the data set. And the second graph shows the activities by user, where you can see which users perform each activity most frequently. So when it comes to training our model, we used a very similar approach to the fog data set. So it was a sliding window approach, except this time we would have to use 15 data points to match the sampling rate of the fog model. And to go with the threshold for window classification, we decided to look at the mode or most frequently occurring annotation of each window. And we decided to use feature engineering instead of the TS-Fresh library. So we decided to go with computed features for the normal data, the fast Fourier transform data, and finally data where the power spectral density has been computed. So with these three sets of data, we would compute the mean, standard deviation, average absolute deviation, minimum acceleration, etc. So just to recap on our methodology and a few novelties with this project, we do want to say that there have been a few studies, as can be shown by this table, that have used our DAFNet dataset or have collected their own data to try to train models. And we wanted to talk a bit more about some unique things we did with our approach. So for example, we looked at the power spectral density to improve model accuracy. We also used TS-Fresh to analyze over 600 different features, which is a novel correlational approach. We also used an additional model activity recognition model for multitask learning to improve fog model specificity. And we also looked at the use of ensemble models, as we mentioned before, which can improve accuracy. And one thing that's a pretty large step forward with this project is the implementation of an app. Since to our best knowledge, we didn't find an implementation of a fully functioning app for detection of freezing of gates. So that's what we wanted to do in this project. And in addition, we also use the load threshold to include windows that occur right before a fog event to hopefully predict fog before it happens. And these two links are the GitHub links to our code. And this was a pretty big project. So we had over 5,000 lines of code in total with a application backend and front end. So moving into the results of the fog model and activity recognition model. So as we mentioned, the fog model was trained with the AdaBoost or adaptive boosting model with a random forest classifier baseline and trained and tested in using 5-fold cross-validation, as you can see here. And this is an example of the data after it's been Fourier transformed, where you can see that the x-axis is each accelerometer point and the y-axis is the frequency. Where it was originally raw accelerometer data, it has been transformed into frequency. And you can see that the signal is symmetrical. And then we moving on to the freezing of gate. So after we trained this model, we found that the model showed an 87% accuracy in distinguishing fog windows versus non-fog windows. And although it's pretty hard to compare our model to others, since we did use a very different approach, we believe that the model does have a high validity, since the DAFNet study achieved 73% sensitivity and we achieved 77% sensitivity. And in another way to validate our model is to use LOOCV, or leave one out cross-validation, where essentially the model is trained on all but one point in the dataset, and the performance of the model is evaluated for that one point that was held out. And this process is repeated for each data point in the dataset, and this more accurately simulates real-world testing. After using LOOCV, we found that the model had an average accuracy, a macro average of 88% and weighted average of 88% in detecting fog. So for the activity recognition model, as we mentioned, the goal should be the model should distinguish walking from jogging from sitting and standing. And these graphs show the raw accelerometer signals from the data set, where you can see walking and jogging clearly have higher signal frequencies and amplitudes from sitting and standing, as you would expect. And for the results of training our XGBoost activity recognition model, we found that the 5-fold sensitivity was 88, 86, 99, and 97% in predicting walking, jogging, sitting, and standing, respectively. This model was also tested at 3 different window lengths, 15, 50, and 100, to identify the best window length. And what we found was that when it comes to measuring the F1 scores, the window length did seem to improve the model's ability to predict walking, but had a negligible effect on the jogging, sitting, and standing. And overall, the model was performing well, since all of the metrics were above 90% for the metrics, except for the walking at 15 and 50 rows. So yeah, now
Okay.
I'll Paul.
Yeah. Okay. So moving on to methods for app creation. So the main components we used were for front end, we used React Native CLI and Expo CLI, which allowed for compatibility between both Android and iOS. However, we've only done testing with iOS, so it's only compatible with iOS so far. And for backend, we actually changed from Node.js and Express.js to Flask, which is a Python-based backend program. And an additional tool we used was Expo Sensors, which was used to obtain accelerometer data from the iPhone. Okay, so one of the main tasks of the backend is data preparation. In this project, the accelerometer data comes from the iPhone, and the backend has to be able to compute 156 features based off of this accelerometer data. So these features include complex methods such as Fourier transform, and these complex functions are pretty hard to implement with language like JavaScript, where there aren't that many sophisticated libraries dedicated to computing statistical information. However, Python do have libraries with these functions, such as NumPy and SciPy. And therefore, instead of using the previous Node.js for backend, which runs on JavaScript, we actually decided to use Flask, the Python-based backend. In addition to that, the application can now make predictions based upon accelerometer data from the iPhone. Feature engineering has been implemented for both activity recognition and fog recognition, and we'll go into more depths of the actual performance of the application. However, to summarize the status of the application, the app can now predict user activity with high accuracy, and also fog instances with high accuracy. And there's also minimal latency with the activity recognition model and the fog model, taking only about 1 to 2 seconds between predictions. Okay, so here's the overall structure of the application. The flowchart starts at the block labeled accelerometer data of the phone. So as you see, the accelerometer of the phone is collected through Expo sensors, and every 100 milliseconds, the accelerometer data is sent to the backend. The Flask backend will compute the features and put this data through the activity recognition model. If the activity recognition model predicts that the user is active, meaning that the user isn't still and they're walking or using a staircase or jogging, the accelerometer data will then be sent to the fog prediction model, which will use TS Fresh to compute the features and make a prediction. This prediction is sent back to the front end as a return to the initial post request. Okay, now moving on to the testing of the application. So here's a quick video.
Hello, I'm Paul, or a bit Paul, and I'm here to demonstrate the application. So the application is running on my computer right now, and I'll quickly just put the phone in my pocket. And right here on my computer, you will see the prediction. So right now, as I stand still, like so, the prediction being made is that I'm still. And as I start walking, now I'm walking right now, and look, we'll say I am walking, and then I'll stop. Those quick accelerations do cause some errors, but now it's still, as I'm still, and as I start walking again, walking, and now I'm back where I started from, and as I stay still once again, it will say I am still.
Okay, So that's essentially what the application can do with the activity recognition model. And now, okay, moving on to our accuracies during testing. So as you see, the model with the window size of 100 did the best with 88% accuracy. And also one of the things we realized was that the model had slight errors during sharp turns. For example, turns with angles greater than 160 degrees often led to errors where the model would predict the user was using the stairs. This is most likely due to similar nature between sharp turns and climbing a staircase, where in both scenarios, a feet works as a strong pivot point to move the body. And so the next slide will show our actual accuracy without these sharp turns. So if we disregard these sharp turns, our models performed very well with the window size of 100 having 96% accuracy, and all of the other ones having more than 90% accuracy when detecting walking. And also we also tested the fog model, and then testing the fog model for 5 minutes showed an accuracy around 92% in classifying fog versus non-fog events. And when testing, I actually essentially just mimicked the previous video shown, where I would simulate a Parkinson's patient having a fog episode. So I would be walking normally, quite slowly, and then I would start shuffling my feet, and essentially end up being completely still. And then further testing and testing with real patients needs to be done to fully validate the fog model. However, through our simulated testing, it's doing quite well.
So just to conclude, in our project, we were able to successfully create a machine learning pipeline with an integrated and scalable iOS prototype application that can be used for activity recognition and freezing of gait monitoring in Parkinson's patients. Upon LOOCV and fivefold cross-validation, the AdaBoost machine learning model was able to achieve high accuracy rates of 87% and 88% respectively in classifying these fog events using the training dataset. The activity recognition model with an XGBoost framework achieved F1 scores of 93, 94, 93.4, and 89 in classifying different activities such as jogging, sitting, standing, and walking respectively when validated with real-life testing.
So since we, and for the limitations and our future plans for the program, since we did go with a sliding window approach, this may have decreased our model accuracy, since overlapping windows means that every subsequent row in the transform dataset has some information from the data in the previous window as well. Additionally, we could also just improve the overall accuracy of the fog model by using an active learning approach, meaning that it would take data gathered from the individual user and use it to improve the overall model. Also, as we were testing the app, we noticed that there was some amount of app latency. So we're considering using smaller sliding windows. But if we do that, this would mean we wouldn't always be able to capture the full duration of fog events, which are usually pretty long. And lastly, since app development is in a preliminary stage, we still need to create a UI. And since we eventually plan to take our app and publish it on the App Store, it would also be very important to have a user-friendly UI that's accessible.
Okay, so moving on to, these are our main sources. As you can see, they're in the APA format. Throughout the project, we made sure to put sources for every picture and cite every information that we used. We specifically, and then as you can see, that's the first slide. And then finally moving on, this is our teamwork. This is how we split work throughout the year to work on this. Starting off, Aditya built and tested the machine learning models. Paul coded and tested the application and the app. I wrote and I reviewed literature and made the presentation. Aiden was a writer too, and he got into contact with Parkinson's patients for future testing, and he also contacted them for insight regarding the disease. And Amandeep was a UI designer. He wrote the paper and he also made the presentation. He worked on debugging the code when it came to coding the models. And that's it. Thank you for listening. And yeah, any questions?
I can jump in. Did you look at any non-sliding window techniques when looking at the time series data coming off of the inertial motion units?
I
So,
can answer that.
oh yeah.
So first we actually instead of using sliding techniques, sliding window technique, we actually used just a pure RMN through, I think like 200 window size essentially, but without the sliding technique, and yeah, it performed quite poorly, having like 70% accuracy. So yeah.
And to add on to that, we tried to use like anomaly detection or change point detection algorithms, where essentially the change point detection is where in a series of data set where, let's say, the annotations are like 0, 0, 0, where there's no fog, and then all of a sudden it switches to an annotation of 1. So change point detection is essentially where we try to identify where that change point occurs. And we found that it's kind of difficult to do change point detection with like collective anomalies where, you know, if you take a single acceleration value during a fog event by itself, that may not actually be an anomaly, but like together with additional like fog events, it may be an anomaly. So that's why we decided to just go with the sliding window instead, since it would be a bit more easier and also more accurate to implement.
Sure. In the report, you talked about testing only with data from one subject. But I think you applied that then to many subjects. And I'm curious why, or what you think is going on, that it seemed to be more accurate to use one subject than many subjects in your training set.
Yeah, so I can take that. So for the activity recognition, so again, we had around 36 users for the training data set. So that one, the way we would kind of like evaluate the model is like, for example, you would train the model on some data set and test it on the other portions of the data set. But for the fog model, we honestly, that was also one limitation to our project, is we only use data from one subject, because we found that trying to use a combination of data, or like trying to combine a lot of data, would decrease the model accuracy. So and this might be because a lot of different users may have different walking styles, which the model may be hard to predict, and the severity of their fog episodes may also play a role. So that's why right now we're currently working on an active learning approach, where we have this model, which, although it's trained from one subject, it can't really generalize to new subjects. So we're implementing an active learning approach where the model is good for a baseline, and then we can add on to that model by learning the specific activities of a user if the user inputs data, and the model can hopefully be more personalized through that method, if that answers your question.
Thank you.
Yeah.
A very nice project. I kind of see one half is the machine learning and detection, but then you did a lot of effort on the software engineering to actually make a deployed app with Android and iOS, with the sensors and the data collection. We worked on a project a while ago for the city of Boston to detect street bumps from accelerometer data from citizen mobile phones. Given that as an example, you have this whole pipeline. Can you think of, just off the cuff, I'm putting you on the spot, 3 other applications using phones and accelerometer data with your pipeline, but instead of detecting freezing of gate, you're detecting something else? Just as putting you on the spot.
Okay, I can answer that. So there are a lot of existing apps that already use this. So like a great example would be like your people's Fitbit, where they essentially where they monitor person's like activity, right? So that's essentially our activity recognition model. And another thing is this is actually, it's quite similar to our thing, but a lot of time there are applications for sleepwalkers that I've seen previously, where they essentially have a device attached to them, or it could be a phone. And during the night when they're sleeping and they start walking, there would be like an alarm waking them up. So we can also use our application to do that. And let me think of another one. I'm not sure.
I think I could add on to this as well. So, as you said, the accelerometers in the current framework that we have can be used for plenty of other diseases. So, starting off, it could be used for epilepsies. These accelerometers can be tuned to detect the seizure activity in patients with epilepsy. And as we said earlier, with Parkinson's disease, whenever you detect an extreme fog incident, it contacts with any medical clinic or personal family member to get into safety. The same thing can be applied for epilepsy as well. We just need to tune it for epilepsy data and detect seizures. And then this could be used to like contact a family member during a case of an emergency. And then these accelerometer data can be also used for other things. It could be used for sleep disorders, as Paul was adding on to it about how there are sleep trackings in devices like Fitbits. If you can scale the application of this project, it could be used to detect sleep disorders and insomnia and those kind of things. So those are some of the practical applications where this framework could be extended to.